Yeah, yes, sir. Yes, sir. I'm here. Yeah. Yeah, sure, sir. Sure. On me. Can you able to see my slides? Yes, sir. So, good morning to everyone. This is Dr. K. Kamalakannan, postdoc research fellow from Institute of Plasma Research, Gandhinagar, Gujarat. So, my title of the presentation is related to the past annihilation studies on nitrogen implanted NK4SCC materials. Actually, this research work is completely collaborated with the DAE sponsored research project and collaborated with the IGCAR Kalpakam, Institute of Plasma Research, and IUS in New Delhi, University of Madras. So generally, I will present the implanted induced defects. So that kind of things using the past and studies, and as well as I have to correlate with this Raman analysis. So these are my outlines. Just I will present the results what happens after the night's implantation for SCC materials using past and Raman. So the main objective is so normally the thermal diffusion process have some limitations because we can't achieve more saturation limit and is have saturation limit we need to get more concentrations so that we have to we can't achieve using normal thermal diffusion process as well as sometimes if we need PN and PN multi-layers so that's we have to form in the layer by layer structures. So this is also not possible for the normal conventional thermal diffusion process, so we have to go with the alternate methods that is called ion protection procedure, which is forcefully we can implant the ions like nitrogen, aluminum, and we can modify the energy and concentration. Everything we can achieve it because we have to do it in forcefully. But so what happened? So due to these ion irradiations, so these produces the defects like some crystal ACC to the amorphous ACC. So we have to study what happens each and every steps during these irradiation procedures. So, due to the different mechanisms, so called electron nuclear stopping mechanisms, produce various type of defects starting from the surface to the particular depth where the ion go and sit. So, so like this, so after amorphization, we have to recover the defects and we have to get the pure crystal and activate the dopants. Like if you are implant a nitrogen and it will become an N-type layer. So we have to make it precisely. So that we have to do this after annealing. So each step, okay, so each and every step for the different annealing temperature, different energy of the implantation. So we have to study what kind of parameters are changes in especially the defect structures. So I am focusing on the defects. The reason is defect have the more applications. So like some qubit application also we can use this, especially for the silicon carbide based defect structures. So particularly I have to analyze the what is type of the defect, where it will be present, and what is the size. Everything we have to tell. So that's why I have to move this particular one. So I restricted this particular work into nitrogen only. So I'm not going with any other steps. Okay, so why I choose silicon carbide? Because silicon carbide is the very hardest material, as well as it have the various different properties. We can utilize this particular material for the various applications, especially high temperature, high pressure application. And simply in Inter India, in that in plasma research also we are considering the international thermonuclear energy reactor. So for that case also it have some nuclear applications like for the first world carding material, fusion reactors, as well as it can be used in the plasma moderator. And some kind of cases, these particular material, especially the defects of this material, used for the quantum applications like qubit related things and quantum information, quantum cryptography. Lot of applications is observed in this particular SAC. So, and one of the major application is SSC polytype. So, during the growth process itself, it produces the different polytypes, starting from cubic to hexagonal, even rhombopedal structures also. So, what I mentioned, this 4H means 4 means the number of stackings. Okay, like it's have the 4 bilayer, it will be there, and H is the hexagonal. So, what is the difference between these hexagonal to cubic or rhombopedal? If the electrical property will be varying, like from the cubic, it had having the band gap value around 2.3. If you go this hexagonal, fully hexagonal structure, it goes 3.3. So this notation is called Ramsel notation. So I use 4SSAC because it is having the huge application compared to any other material because it has high saturation electron velocity, high thermal conductivity, and a lot of applications compared to any other structures. Okay, so what I do, as I mentioned, I have to use the ion irradiation procedure to implant the material. I used that 150 kV gaseous ion implanter, which is available in IGCAR Kalpakam, and I used 75 kb of the ion implantation for the porous AC materials. Ion implantation, as we know, it's not trial and error. It's not a trial and error method. So that's why you have to go with some simulation methods to predict what is the energy we have to use and what depth we needed and what's the constancy we needed using the shim and trim. Okay, so these are the some simulation code. So based on these, we have to fix what energy we choose. So based on the stream analysis, these are the stream setups. Okay, like what's the code in the first page, how we can calculate this particular one, and so finally these are the simulation. So we got this particular things. So based on this analysis of the stream and trim, so I chosen the nitrogen with that 75 keV implanted in the 4S SCC material with the only 10 per 6, 10 per 16 ions per centimeter fluence rate. So typically it will go around 130 keV plus or minus 14 nanometer staggering. Okay, so these are the some simulator values. So this I needed because I have to implant another material on top of that particular layer. So that's why I fixed this particular range using the simulation principles. So okay, fine. So of course, the simulation results we shows like this. The maximum ion range of particular things is, as we mentioned, it's 130 keV. But even though it's go beyond the ion range also, but maximum ion range it's around 130 plus or minus 50 nanometer. Okay, and of course the damages which is produced before the ion range maximum, which is called vacancy maximum. Okay, so and this parameter like this pink color is positron depth profiling for this case, and which positron energy will be chosen for this particular one. So that's a fix for this case. Okay, so as I mentioned, why I need the defect characterization means because it can be utilized for the various applications, and as well as I use these defect identification using Raman and partial analysis, especially the Doppler bonding spectroscopy technique, right? So this is the technique block diagram. Usually we are using sodium 22 isotopes, which is moderator after the tungsten moderator. So of course, recent studies has already mentioned that SiC can be utilized instead of that tungsten, and after that it will be secondary positive will come, and we have to accelerate again, and we have to implant inside the material, and it will be annihilated, which gives the 511 keV. These 511 keV have some different values. It's not exact 511 keV, some plus or minus some 1 or 2 keV. So that's the broadening value. Using that broadening, it depends on the momentum distribution of the material, electron momentum especially inside the material, which is depends on the defects, type of the defect, what's the position. So these are the various different Pascal setups. Actually, I am using the Doppler bonding only, especially the variable energy Doppler bonding, which means we have to vary the energy of the implanted positron. So, the positron will be implanted with different energy, like okay. So these are the setups. So positron implanted inside the material, it will be go at a particular depth, and it will find out the vacancy where it's presented, and after that it will be annihilated, which gives the gamma rays. So these gamma rays, especially, we can tackle the different energy, and we have to get that particular plot like this. So this is the Doppler bonding setup which is available in IGCAR Kalpakam, and the center parameter is called S parameter, simply called the SAVE parameter, and both the high momentum region, which is called both sides, this one D and F, it's called W parameter. So this W parameter is sensitive to the core electron contribution, and this S parameter valence electron contribution. Most probably this is related with the open volume defect. This W parameter related with the chemical surrounding of the defect sites. Okay, so using this particular one, for each energy it will go each S value, and the step size we are using 0.5 keV, starting from 0.2 to 0.5 keV step size and up to 22 keV. Each energy give the each one value, so each like S parameter, and this completely it's platted, and we have to get that particular type of things. After that platting, we have to fit this particular one using the variable energy Pascal fitting method to find out what is the type of the defect and where it will be presented. Okay, so this is the result for the Doppler bonding, variable energy Doppler bonding spectroscopy. So these each dots is having that each energy, each S parameter from taken from that particular thing. So after the particular counts is reached, we have to get that each data, and it's go up to 22 keV. It takes around 1 to 2 days for complete setup for this particular things. And after this data, we have to fit this one particularly using the variable energy Pascal fit to find out the what's type of the defect. Of course, that pristine sample, which is the bottom one, is unirradiated one, and as well as homogeneous, and as well as this is what is that defect free nature. So that's why we have to use the single layer fitting, so which gives that of course it's don't have the defects. Let us consider that particular things. After implantation, of course, the S parameter increases in the surface region, and if it is going in the deep region, the mean implant depth also we have to return here. Okay, so after the deep region, of course, it's matched with the pristine value. Yes, sir. Yes, sir. Yes, I'm going that particular one. Yes, yes. So all the fitted results we have to finish this one and getting the different values and the type of the defects we have to analyze the final results we give like this. Okay, what is the different type in the different region, especially die vacancy which is presented in the surface region, deep region which will be in the mono vacancies. So even Raman also we have to get that these this amorphized regions also we have to analyze. So and the particularly the measure of disorder we have to quantify this particular using the particular peak. So that value is also correlated with the stream analysis. Okay, so summary of my work, of course, we done the type of the defect where it be presented and what is the variations which is observed. So thank you so much. Thank you. Thank you, sir. Thank you. Thank you. Thank you so much. Sure, sir. Yes, yes. Thank you, sir. Thank you so much. Thank you. Thank you. போங்கடா டேய், 5 நிமிஷத்துல என்னத்த பா சொல்ல முடியும்? போங்கடா, முடிஞ்சு. ஒன்றும் கேட்கலையா? எதுவும் கேட்க மாட்டாங்க. கேட்க கூடாது சொல்லி வச்சிருக்கோம். சாப்பிட ரெடியா இருக்கு. சாப்பிட ரெடியா இருக்கணும். நானே சாப்பிட போகணும்ல. வெளியே வந்தாச்சு. ஐ எம் ஐ எம் ஹியரிங் யுவர் பிரசன்டேஷன். ஐயோ யாரையா இவங்க மாட்டிட்டேன். சரி, சாப்பிட போயிட்டாரு. 1 மணி ஆச்சுல. ஓகே பாய். அதுக்குதான் ரெடியானது. வேற என்ன இருக்கு? போட்டோ எடுக்கிறீங்களா? சூப்பர் பா. கிளாரிட்டி தேவையில்லை நமக்கு அது இதுக்கு.